guys. This is our first video lecture for TRIG. Hopefully it's clear. If it's not clear, if you can't see something maybe because of lighting, let me know and I'll work on it for next time. We are going to go to section 7.5 today. This is where the remainder of our sections is starting. You guys, we're going to look at TRIG equations today. So going back to algebra, we haven't really solved for x in a long time. We've been evaluating trig functions, graphing them, doing all this stuff, but a lot of times we have a variable and we never solve for it. So a lot of times we can find the sine of theta, but we don't know what theta is. Yes, we have our inverse functions for exact angles, and we'll use those today. But you guys, we're actually going to be looking at equations with certain values for variables that we have to find. One thing I want to note, when we get our answers today, we're going to be in radians, not degrees. I know we love degrees, but we do have our unit circles so we can see the radian answers, so it won't be so bad. Now, as we get started, I'm going to start with a pretty easy example. So if I have 2 sine theta, let's see, 2 sine theta minus the square root of 2 equals 0. This is my equation. So notice theta is my unknown, and I'm actually going to solve for theta. Now, I can't do it yet, but if I isolate the sine function in this case, then I can solve for theta, and I'll show you how to do that once we get there. All the rules of equations apply whether you have trig functions in the equations or not. So I can divide by the same thing on both sides. I can add, subtract, multiply. As long as I do it to both sides, then those rules stand. So let's get started. The first thing I would want to do, like I said, I can't actually isolate theta right now, but I can isolate the sine of theta. So I've got this minus root 2 here. I'm going to pull that to the other side. So I'm going to add root 2 to both sides. Then what I'll have is 2 sine theta equals the square root of 2. Now, theta is still not isolated yet because of this 2 here. So let's divide by 2 on both sides. And I get sine theta equals the square root of 2 over 2. All of your answers will be exact, which means you're going to go to the unit circle to find your answers for theta. Now, remember I said our values are going to be in radians. We always want to be really careful to look at the interval our answer needs to be in, because I know that sine theta equals square root of 2 over 2 at pi over 4 and at 3 pi over 4, but I could find an infinite number of answers by keeping going around and around the unit circle. So that's why we have a restricted range for our answers. Notice this one is from 0 to 2 pi. That means looking at the unit circle, one full rotation, where is the sine of theta square root 2 over 2? So that happens at 2 places within that one rotation. It happens at, like I said before, it happens at pi over 4, and it also happens at 3 pi over 4, because sine of theta is still positive at 3 pi over 4. You guys, we have to pay attention to the sign of our answers. Notice that sine has to be positive root 2 over 2. That's why I only get a first quadrant and a second quadrant angle as my answer. If I was in the third or fourth quadrant, the sign there would be negative root 2 over 2. So I can only use the positive ones. So for this example, I have 2 answers for theta, and I would input those and be done. Notice that solving for the trig function here was a lot like solving a linear equation. If this had been an x, I could have isolated x by subtracting, adding, multiplying, dividing, the same thing on both sides. You guys, this is our basic form of the equation where we solve using linear techniques. I want to do one more like this. So what about this one? I've got the cosine of theta plus 4 equals 3. So again, I'm solving for theta, but first I need to isolate the cosine of theta, and then I can go to the unit circle to look for my answers for theta. So on this one, it looks like all I need to do is subtract 4 from both sides. And I get the cosine of theta equals -1. You guys, let's use the same interval range for this one. Let's say that we are on an interval from 0 to 2 pi, which is 1 full rotation. So I go to my unit circle. Again, remember cosine are the x values on the unit circle. So if you're looking at your unit circle, then you find the spot within 1 rotation where cosine of theta equals -1. You guys, that happens at one place on the unit circle, and that place is theta equals pi, or 180 degrees, but we're using radians. So let's walk a little backwards through it. If your angle is pi, the cosine of pi equals -1. That's true. I know that all I did was subtract 4 from both sides, which means that this is true where we started. Okay, so notice on the first question we did have 2 answers, and on this one we just have 1. It didn't say cosine is positive or -1. If it did, I would have 2 answers, but there's only one spot where cosine is -1. So when you're doing these problems, even though this one looks a lot like the sine one we just did, that doesn't mean they're always going to have the same number of answers. It depends on this value right here and how many times it occurs on the unit circle. All right, so this is another linear type equation. I'm going to do one more linear type equation. These were both sine and cosine. Those are the easiest to find on the unit circle because those values of x and y are actually directly on the circle. But what if we don't have sine or cosine? Let's say we've got a tangent question. So I'm looking at tangent theta -1 equals 0. Okay, so I can see, again, I'm going to solve by adding 1 on both sides to isolate the tangent. So I get tangent theta equals 1. You guys, once your trig function is isolated, that's where you go to the unit circle and find your answers for theta. So on 1 rotation, so between 0 and 2 pi for tangent, remember that tangent is always y over x. You can also think of it with the quotient rule. So another way to see tangent is sine over cosine. And I'm going to have to use this fact to find the places where tangent is 1. You guys, on our unit circle, we find the places where y and x are the same, right? If they're the same and you put them over each other like y over x, or you call it sine over cosine, that's where you're going to get the 1, right? So there's one place where that happens in the first quadrant. You guys, at pi over 4, or the 45-degree angle, you guys, why does it happen there? Well, because the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is also root 2 over 2. What happens when you put those as a fraction, sine over cosine? That's where you get 1. So if you're looking for a tangent that equals 1, looking for those places where sine and cosine are the same. Now, tangent equals +1 in one other place. You guys, in the third quadrant, where sine and cosine are both negative, you would put them over each other and they would become +1 again. So in the third quadrant, your reference angle pi over 4 You guys, that's going to be the 5 pi over 4. So this one has 2 answers for theta within our 1 rotation, so between 0 and 2 pi. We have pi over 4 and 5 pi over 4. Those are the only two places where tangent equals positive 1. Be careful, again, with the sign. You don't want to put the second or the fourth quadrant pi over 4 angles in there because tangent's -1 in those quadrants. So we're really careful with our signs. We're making sure we're staying within our interval. But once you isolate the trig function, you really are just looking at the unit circle for your answers. Okay, so these 3 examples, I mentioned that we solved them linearly, which when you're solving a linear equation, again, you just do the same thing to both sides and you isolate what you want to isolate. But you guys, not all of our equations are going to be able to be solved like that. So let's look at a case where our trig equation is not linear, and I'll show you how to tell the difference. So what about this one? I have 4 cosine squared x minus 3 equals 0. You guys, why do I know this isn't a linear equation? Well, because it has a squared, right? The term that I want to isolate, the trig term here, is cosine squared. Because of that, I'm just going to have to be super careful. So the first thing you would do when you look at this, yes, there's a squared in there. Yes, I'm going to have to be really careful about it. But that minus 3, I can still pull that over to the other side. So let's do that. Let's add 3 on both sides. Then I have 4 cosine squared x equals 3. From here, do you think, even though there's a squared in there, I could still divide both sides by 4? Yes, of course, it's still an equation. Let's divide by 4 and isolate that cosine term. So, dividing both sides by 4, I get cosine squared x equals 3/4. All right, this is where it gets different, right? Because if this was just cosine x equals something, that's where I would go to my unit circle. But you guys, we have to take an extra step. I'm trying to isolate cosine x. If I keep the squared in there, I can't go to my unit circle and find those values. So we're not totally done isolating the trig term. I have cosine squared over here, but I really need just cosine x. So how do I get rid of a squared? Well, I take the square root of both sides, right? Let's square root both sides, and we have to do it very carefully. So when I square root the cosine squared, what I end up with is cosine x. That's what I wanted to isolate. So I got that. What's on the other side? I'm square rooting a fraction. I know that I can square root the top and square root the bottom separately, so that's what I'm going to do. On the top, I have the square root of 3. I'm just going to leave that as the square root of 3. And on the bottom, I need the square root of 4, which is 2, so let's call it 2. Now, one very important thing, I square rooted both sides, which means I need to consider that this is a plus or minus root. So on these squared functions, you are going to square root both sides. Make sure you do the plus or minus, or you're going to miss out on some answers. So plus or minus square root 3/2. And yes, we did square root separately. Technically, yes, the top would have a plus or minus and the bottom would have a plus or minus, but we can apply it to the fraction as a whole. So I get plus or minus root 3/2. That's what cosine x is. Remember, my goal is to solve for x in this case. I know last time it was theta. We kind of switch back and forth. That variable can be anything. So in this case, x is the angle I want to solve for. I go to my unit circle. Where is cosine square root 3/2? You guys, cosine is square root of 3/2 at pi over 6. But you guys, I also consider the places where it's negative square root 3 over 2. You guys, in the second quadrant, there's a place like that, right? It's at 5 pi over 6. In the third quadrant, it's also negative, but it's going to be at 7 pi over 6. And in the fourth quadrant, we're back to positive root 3 over 2, and that's the 11 pi over 6. So you guys, because of the plus or minus, we have 4 solutions here. Don't forget the plus or minus, because if you were just looking for the positive places, you would only get these 2. If you were just looking for the negative places, you would have only gotten those 2. So you would have half a solution. So be careful with the plus or minus. This x is actually 4 answers. You guys, one thing that I really like about the ALEX system that we're using is you get to practice a lot. So when you're doing your homework, and I know you've probably figured this out already, it gives you questions on each topic, and you have to, I'm going to say you have to answer 3 correctly before you can even move on to the next topic. So it does give you a lot of practice. Alex wants to make sure that you have a good understanding of the material before we move on to the next. So that's one thing I like about it. So you guys, you have questions that look like all of these examples that I'm doing today. And it won't let you move on until it knows that you know how to do it. So let's see, let's look at some different types. So in this example, I have in parentheses 2 sine theta plus the square root of 3. And then next to that, in another set of parentheses, I have 3 cosecant theta minus 2 root 3 equals 0. So this looks a lot different. Now, when I look at a problem like this, it's not going to be able to be solved with the linear steps that I was doing, trying to isolate the trig function by getting it on one side. One thing that throws a wrench in that problem is we have 2 trig functions. So I somehow need to isolate them both. So when you see a problem like this, it's actually set up so nicely for us, because notice we have an equals 0 on this side. What happens when I have an equation where something times something equals 0? If you don't remember, the way I solve equations like this, we call them factored equations. I have factors multiplied by each other equals 0 on the other side. The way I solve it is I can take each factor separately and set it equal to 0. Because if you have a statement like this, the only way that 0 can actually be your answer is if one of these factors is 0, right? So I don't know which one it is. It could be either, so I set both equal to 0. So let's start with this first factor. I'm going to take it out by itself, and I have 2 sine theta plus root 3 equals 0. So I take this one, set it equal to 0 on its own, and then let's take the other factor, 3 cosecant theta minus 2 root 3 equals 0. So basically I've separated this into 2 equations, and I'm going to get answers from both equations. All right, so let's start over here. This one looks a lot like that first one we did. Let's subtract root 3 from both sides, and I will get 2 sine theta equals negative square root of 3. Divide both sides by 2. And I get sine theta equals negative root 3 over 2. I can solve this. Like I said, this is just like the first one I did. So I think about my range. I'm going 1 full rotation, finding all the angles where the sine is negative root 3 over 2. So you guys, sine is negative in the third and the fourth quadrants. It's root 3 over 2 at the pi over 3's. So my answers for theta from this factor are going to be theta equals, so reference angle pi over 3, but it's negative, so in the third and fourth quadrant, we're looking at 4 pi over 3 and 5 pi over 3. So you guys, these are two solutions. They only came from the first factor. So yes, these are valid solutions, but I'm also going to have solutions from this second factor. So because I have a really small board, I'm going to have to erase something. So I'm going to let that sit for a second. So if you need to keep writing before I erase, do that right now. And it's super weird talking to nobody. Okay. I guess you could have always just paused it. Okay. Anyway, so I'm going to erase now so I can solve this second factor. So these are two of our answers for this problem. All right, so let's solve this factor. The first thing I would do is add 2 root 3 to both sides. Now I have 3 cosecant theta equals 2 root 3. So we're here. Let's divide both sides by 3. And I get cosine theta equals 2 root 3 over 3. This one's going to be a little harder for us. Actually, it's going to be a lot harder because we're not used to knowing values of cosecant. But when I'm looking at a cosecant or a secant, so one of those reciprocal functions, what I do is pick out familiar numbers. So when I see this, I see a root 3. I do see a 2 in there somewhere. I'm thinking, well, maybe this is just root 3 over 2 flipped over. Well, let's check. So it's a question. I don't know if it's true or not, but what if I had root 3 over 2 and flipped it over? Its reciprocal would be 2 over root 3. But what would I do? I would rationalize it, right? I'd multiply top and bottom by the square root of 3, and I would get 2 root 3 over 3. So what I'm saying is that for a cosecant to be 2 root 3 over 3, that means its reciprocal. What is the reciprocal of cosecant? Sine. That means what I'm looking for are places where sine is root 3 over 2. So again, I know there's a lot to process there. If cosecant is 2 root 3 over 3, I find the reciprocal of that. I found the reciprocal, it was root 3 over 2. So I'm looking for places where sine is root 3 over 2 because the reciprocal is 2 root 3 over 3. Okay, so be really careful. Make sure you are pairing up the correct reciprocals. Remember, sine goes with cosecant in the reciprocal pairs. So where is sine? Positive root 3 over 2. That's what I'm looking for. Again, that's at the pi over 3's, but this time I am looking for positive root 3 over 2. So I'm going to get pi over 3. That's the one in the first quadrant where sine is positive. And I'm also going to get 2 pi over 3 because that's the second quadrant where sine is positive. So let's remember the answers I got before. So in the first factor, I was looking for places where sine was negative root 3 over 2. So answers I got were the third and fourth quadrant. I got 4 pi over 3 and 5 pi over 3. So this was our answer from the first factor. So from this factor, I got these two answers. From this factor, I got these two answers. So you guys, that means my answer is all 4 of them. So you take your answers from both factors. Okay. So, you do have questions that look just like that. You're having two factors set equal to 0, take each one of them and set each one equal to 0 individually and solve like we have been solving. Okay, let's see what else we got. So you guys, your last set of problems are going to include a couple of identities. Yes, we just did identities. I know we want to leave that in the past. But these examples are going to be the double angle identities. So I'm going to write those in a place. So you guys, our interval is going to be from 0 to 2 pi throughout. So I'm going to take that off because we could say it's understood. And I'm going to give us a couple double angle identities that we'll need. So remember the double angles, we had cosine of 2x equals cosine squared x minus sine squared x. Remember, it's an x here, it could be a theta, it could be any variable, right? We also have sine of 2x equals 2 sine x cosine x. So you guys, these are identities we learned for the last test, right? When you're doing your homework, I would recommend having a note card with identities on it with you all the time so you can use any of them that you need. Also your unit circle. Obviously today we're really leaning on the unit circle heavily. So unit circle, note page, whatever, with identities, really important. Okay, so I said we were going to use these to solve an equation, so let's do that. So one thing that I noticed in Alex, when I do a double angle, I always put parentheses around the 2x. They do not always put parentheses around the 2x, so I'm going to write it like they do. I don't want that to throw you off. I know it's just a pair of parentheses, but when you get used to seeing things a certain way, I want to make sure that you know this is still equivalent. So I have cosine x plus cosine 2x equals 0, and I need to solve for x, of course. So again, I can't isolate the cosine. Here's what I can't do, and here's what I want to really be careful with you guys about. Cosine x is not the same as cosine 2x, right? I cannot add these together. I can't do some kind of weird 3x, adding the x terms together. I cannot put these together at all because the angle in them is not the same. But you guys, instead, what I'm going to do is go a different route. What if I could take this 2x and write it in a different way? That's where we use our identities. So I say, oh man, I don't want a 2x in my problem. I just want cosine x in my problem. How can I make that happen? Well, look here. I can say, okay, another way to write cosine 2x is to write cosine squared minus sine squared. Now, yes, I'm putting a sign in there and I'm putting squareds in there, so you think, oh, that's going to be worse, right? But it's not worse because notice the argument or the angle is just x. It's more important to me to get all of the angles the same. So what I'm going to do is I'm going to leave this one as cosine x, of course. I'm going to be careful with parentheses. I don't think it's too important on this particular problem, but it might be on another problem. So when you're using identities to sub something in, use parentheses. Just humor me. Okay, so instead of writing cosine 2x, I go to my identity and say, okay, what's another way I can write cosine 2x? I can write it as cosine squared minus sine squared. And I look at it. I say, okay, I don't know if that's the most helpful way to do this problem. Do I really want to put a sign in there? Well, you guys, I could work this out. But don't I remember, I have a couple of extra versions of cosine 2x, right? You guys, cosine of a double angle, so cosine 2x is just the best identity because we have 3 ways that we can write it, right? So I look at this and I say, okay, this is true. I could keep going from here, but what if I could write this to where all I have are cosines? Because I have this cosine, it's not changing. What if I wanted to write cosine 2x in a way where I only have cosines? Can I do it? Absolutely. Remember, and again, you have your reference sheet of identities, so you can find this. What's another way to write cosine 2x? And you look at your identities, and you see that there's actually one that only has cosines in it. All right, so I want you to take a minute and verify for me that you can find this version of cosine 2x. Yes, I purposely used the normal one. I call it the default cosine 2x because it's the one we usually use. You guys, I put it in here. I decided I think I can make this easier on myself. So I went back and I found another one. You guys, I'm going to use this one. Remember this and this, they're both identities, which means they are both true all the time. So instead of writing it as cosine squared minus sine squared, let's try this version. Let's write it as 2 cosine squared x minus 1. This looks better to me for a couple of reasons. One, because I don't have a random sign in there now. You guys, all I have is cosines. And because I have those similar cosines, I'm actually going to do some factoring. So let's look at my next step. I have cosine x plus 2 cosine squared x minus 1 equals 0. The first thing I'm going to do, and it might not be apparent what you would do here, so I'm going to give you some ideas. If you have something like this, you have a squared term and a term that's not squared, try putting the squared term first, just rearranging the problem. So I have 2 cosine squared x plus cosine x, and I had that minus 1 equals 0. Okay, so it looks a little better. We got rid of parentheses, which on this one I know we're not needed. I'm just being thorough. We got rid of parentheses. Notice all I did was rearrange the problem. I've got a squared term, I've got a first power term, and I have a constant. Does anything about this jump out at you as far as factoring goes? Maybe not, and that's okay. But when I see it, when I see a something squared, something to the first power, and then a constant, the factoring technique that I want to use is quadratic. You guys, just, what if this was 2x squared plus x minus 1 equals 0? So what if we didn't have cosines? What if we were just looking at a straight equation with x? When you see something like this, you see the 3 terms. One is squared, one is to the first power, one is a constant, it equals 0. You want to factor using the quadratic factoring, right? Reverse FOIL, if you will. It may have been a while since you've used it, but we're going to have to use it. Just because these are trig functions doesn't mean that that pattern doesn't hold. So you might be envisioning it like this, like a normal quadratic equation. Yes, we have cosines, and that's all right. We're still going to factor. Okay, so you have to be able to recognize that this is a quadratic factoring problem. How do we factor quadratics? Good question. I know I don't think we've had it in this class, so it might have been a while since you've done it. Okay, so when I factor quadratics this way, the first thing I do is I want to think about factors of the first term. And I usually just write them under the first term kind of small. It's kind of my working template. So I've got 2 cosine squared x, and I need to think about factors. So in other words, what 2 things could multiply to make that thing, right? So could I say I could break this up as 2 cosine x times 1 cosine x. If you multiplied 2 cosine x times cosine x, you would get 2 cosine squared x. So what I've done is I found 2 factors of the first term, and I just write them under like that. Now, then we skip the middle term for a minute, we go to the last term. You guys, I need to find 2 factors of the last term. The sign on this term does matter. So what I'm looking for is 2 factors of -1, and there's really only one choice here, right? It's got to be -1 and +1. There's no other way around it. Now, I say, oh, I've got all my factors, I'm good to go. Possibly. You guys, I don't know if they're in the correct order or not, and the order is important. So I'm going to give you the way that I check these solutions. If you have a favorite factoring technique, go ahead and use that. This is what I do. I always check to see if the order is correct. The way I check this is with cross products. So I've got these factors under this number, I've got these factors under this term, and I cross multiply. I say, okay, well, 2 cosine x times 1 is 2 cosine x. Do the other cross product. Cosine x times -1, well, that's negative cosine x. So what do I do with these cross products? Well, I add them together. Take your 2 cross products, add them together. So I've got negative cosine x plus 2 cosine x. What does that leave me with? Well, it leaves me with 1 cosine x. So you guys, what I'm doing here is I'm using cross products, I'm finding them, adding them together. My goal is that when I add those 2 cross products together, I get the middle term in my problem. If I do, I know that I have the right factors and they're written in the right order. And then I can go ahead and continue factoring. So if for some reason you do cross products and you get an answer that's different from this, try flipping the order of your factors, because order really does matter here. But you guys, it worked out the first time for us. So when I write down the factors, I'm going to have a factor here and a factor here. These come from these 2 rows. It can be a little bit confusing because remember, after I wrote the factors, I used cross products to check my answer. But when I actually write my factors down, I go straight across. So when I write them down, I'm going to have 2 cosine x minus 1. And then I'm going to have cosine x plus 1. So these are probably going to be the hardest problems for us because we haven't factored in this whole class. Hopefully you're not too rusty on factoring, but if you are, you will have lots of practice. Alex will not let you go on until you get it, which I love. So I have 2 factors equal to 0. I'm going to solve it just like I did the other one where we set each factor equal to 0. I'm going to write them on this side a little bigger. So I have 2 cosine x minus 1 equals 0. Let's solve that first. So I'm going to add 1 on both sides, and I get 2 cosine x equals 1. I'm going to divide both sides by 2. I'm isolating the cosine x, and I get cosine x equals 1/2. You guys, because I've isolated cosine x, I know this is where I go to my unit circle. I'm looking for places between 0 and 2 pi, so still just 1 full rotation, where cosine x equals positive 1/2. That happens at 2 places. The first time it happens is in the first quadrant at pi over 3. The second time it happens is in the 4th quadrant at 5 pi over 3, because those are the 2 quadrants where cosine is positive. So here's 2 of my answers, but I'm not done because I still have to set that second factor equal to 0. So I need more space, so I'm going to stop for a minute so you can write, or just pause the video. I keep forgetting you can do that. And let's solve for the second factor. Okay, so I have cosine x plus 1 equals 0. Subtract 1 on both sides, I get cosine x equals -1. Go to your unit circle. Where is cosine -1? That's only at one place. That's at 180 or at pi, right? So cosine is -1 at pi. That's an answer. What were our other two answers from the other factor? That's where we got the pi over 3 and the 5 pi over 3. So we have 3 answers on this problem. This was a long problem. This is going to be the worst kind of problem for us. I'm going to do one more with this double angle situation, and then you should be ready to start your homework. Most of our trig equations are really not that bad. Those first ones, you isolate the trig function, and then you go to the unit circle and find the answers. Yes, these are a little bit harder. They involve identities, they involve factoring techniques that we probably haven't used in a while. But just remember what your goal is. Your goal with the factoring, with the identities, is to try to isolate your trig function so you have that last line that you can take to your unit circle and find the values. All right, so this is the last one. Hold on. Okay, so I've got 2 sine x plus the sine of 2x, so don't get those mixed up, equals 0. Okay, so I see the 2x again. You guys, this time it's the sine of 2x. I only have one possible identity to use for the sine of 2x. It's not as versatile as the cosine of 2x, where I can kind of pick and choose depending on what my problem looks like. For the sine of 2x, there's only one thing that equals. I'm going to use that. So I already have this 2 sine x here, plus, instead of writing sine 2x, what am I going to write? I'm going to write 2 sine x cosine x. Again, I know on this one, the parentheses were not needed. I'm still using them. You guys, you never know when you're going to have a minus here. That's what our parentheses are for. No, on this one we don't need them, so let's go ahead and get rid of those. I have 2 sine x plus 2 sine x cosine x equals 0. So I only had one choice for sine of 2x, and it does involve a cosine. I cannot get away from having a sine and a cosine in this problem. So I just deal with it because I don't have another identity choice. But when I'm looking at this, notice there's no squares, so I don't think this is going to be one of those quadratic factoring techniques that I'm going to use. But I am going to try to factor because I have an equals 0. And if you have an equals 0 on one side, it's a good hint that you might want to factor. If I don't have another idea on how to factor, what I do, greatest common factor. What is something I can take out of both terms? Well, they both have a 2 sine x. Why don't I take that out? If I take out 2 sine x from both of these terms, let's see what I'm left with. Okay, so from this first term, it is 2 sine x. If I divide by 2 sine x, what am I left with? Just a 1, right? Second term is 2 sine x cosine x. If you divide out the 2 sine x, what's left? Just a cosine x. I know it's weird to be factoring with trig equations, but factoring works the same. You can take a common term out of all the terms you have, and you can end up with something like this. Okay, so what does it look like here? I've got 2 factors equal to 0. I'm going to do what I've been doing. I'm going to set each factor equal to 0. This factor is just one term. Don't discount that. Still set it equal to 0. It's going to give you some answers. Okay, so the first factor, 2 sine x equals 0. I need to solve for x. Let's isolate the sine function, dividing both sides by 2. Well, 0 divided by 2 is still 0. So I get sine x equals 0. Go to your unit circle, find the places where sine x equals 0. That actually occurs at 2 places. So for this particular factor, I'm going to get 2 solutions for sine. Sine is 0 at 0, and it's also 0 at pi. Okay, so that's 2 solutions coming from the first factor. So I took care of that factor. Don't forget about the other factor. 1 plus cosine x, I have to set that equal to 0 also. So take that to the side. Subtract 1 on both sides to get cosine by itself. I have cosine x equals -1. Go to your unit circle. Where does that happen? We've actually had this particular one a lot today. It happens in one place. Cosine equals -1 at pi. You guys, I have duplicate answers here. That's okay. When you write your answers, you don't need to write pi twice. It just means that it showed up in your answer twice. Okay, so when you would write your answers here, because yes, we got a duplicate pi, your answers are just going to be 0 and pi. Like I said, you don't need to write it again because it came from a different term. Okay, so solutions. All right, guys, like I said, please start working on these homework problems as soon as you watch this because you'll be ready. One thing that's nice is that you can reference this video. You can come back to it to help you do your problems, which is something you couldn't do before. You couldn't just, replay my lecture in your mind. So hopefully that'll help. If you do have questions, remember that office hours for our class are at normal class time on Mondays and Wednesdays at noon. You'll have a link in your email every time one of those office hours pops up. If you need to, click the link, get into the Zoom meeting, and we can talk, and that it's like my office hours. If you don't need to, if you get that Zoom link email and you don't have any questions for me, you don't have to join the meeting. There's no requirement there. It's just those are my office hour times. So talk to me in office hours if you need to. Replay this video as many times as you need. You can stop and go to certain areas when you're doing a certain problem. If you have any questions, let me know. If you have questions with Alex, especially, I know it's new, just let me know. But that's it for this first video.